Now to finish up 5.4, projections, Hilbert space isomorphisms, we'll pick up with the next result, Theorem 5.4.7, which says if set R, consisting of vectors R1, R2, and so forth, is an orthonormal basis for a Hilbert space H, and for vector H, we have H given by the representation sum from k equals 1 to infinity, inner product of H with R sub k times vector R sub k. In other words, these are the coefficients in the representation of H with respect to this orthonormal basis. Then the norm squared of H is the sum from k equals 1 to infinity of A sub k modulus of squared, where the A sub k's are those coefficients. They are the inner products of H with R sub k. In fact, we used this type of representation in the proof of one of the previous results. So we need to give an independent proof of this, but we'll take this as given. The goal now is to show Hilbert spaces with orthonormal bases in the sense of Schauder are unique. That is, to prove the fundamental theorem of infinite dimensional vector spaces, as I call it. First, a Hilbert space with a countable dense subset is said to be separable. So this condition of separability is associated with an idea of dense subsets and countability. It's common to consider this property of separability of Hilbert spaces, and we're interested in separable Hilbert spaces. Indirectly, yeah, directly, not so much. It's another property that we're interested in, but that property turns out to be, as we'll show, equivalent to separability. In other words, Hilbert space H is separable if there's a subset, D, consisting of vectors D1, D2, and so forth, such that for any H, any vector H in the Hilbert space, and for all epsilon greater than 0, there exists a D sub k in this set that's within distance epsilon of vector H. So dense in the usual topological sense. If we were to consider the topological closure of D, then that would include all vectors H in the Hilbert space. In other words, the topological closure of set D is the whole Hilbert space. Now, as I stated, separable, not really the goal. Many texts study separable Hilbert spaces. I say we're interested in Hilbert spaces with Schauder bases. Well, it turns out it's the same thing. So in fact, it's more common to take an approach of considering separable Hilbert spaces. But the reason separable Hilbert spaces are of interest is because they have Schauder bases. And it turns out conversely, Schauder bases containing Hilbert spaces are also separable. And that's what Theorem 5.4.8 says. A Hilbert space with scalar fields of the reals or the complexes is separable if and only if it has a countable orthonormal basis. That is, if it has a Schauder basis. So let's go through a proof of that. Okay, so the plan is to show a Hilbert space with either real or complex scalars is separable if and only if it has a countable orthonormal basis. So first, suppose H is separable. That means a countable dense subset. So let D1, D2, and so forth be the vectors in such a subset of Hilbert space H. We're going to do something kind of Gram-Schmidt processy to modify this countable dense set. For k greater than or equal to 2, define capital D sub k to be the span of the first k minus 1 vectors. Given that, define E sub k, a new vector, to be vector D sub k minus the projection of vector D sub k onto that span, capital D sub k, that span of the first k minus 1 vectors. So this produces a new countable set of vectors, E sub k's, and we've roughly did the Gram-Schmidt process. The Gram-Schmidt process takes a basis and turns it into an orthonormal basis. If you like, it takes a countable basis and turns it into a countable orthonormal basis. Well, We didn't normalize as we go, and we didn't know that we started with a basis. So there may be some linear dependence in this set of vectors, and we might have picked up some of these E sub k's as zero vectors along the way if there was linear dependence in the original set. Then what we're going to do is take those vectors E, put them in a set, capital E, E1, E2, and so forth. We still got countable collection of vectors. We may have picked up some zero vectors along the way. Well, throw those out. Throw out the zero vector if we picked up zero vectors along the way. And then what results is a linearly independent set, linearly independent in the sense of Schauder. And we still have the denseness of this set in capital H. So countable dense subset as well. Apply the Gram-Schmidt process to set E. So that takes this linearly independent set, converts it into an orthonormal set. The denseness allows us to conclude in the sense of Schauder that we have an orthonormal basis in the sense of Schauder of the Hilbert space. So separable implies countable orthonormal basis. Now we need to go in the other direction, and suppose we have a countable orthonormal basis, R, capital R. The set is R1, R2, and so forth. And if we were doing this in Rn, you'd expect the rationals to play a role. In Rn, a countable dense subset is Qn. In Cn, a countable dense subset is, well, n-dimensional rational complex numbers. So we're going to do something like that. It's a little more complicated. We're trying to create a countable dense subset. We're going to give an epsilon argument, but we certainly will see rational numbers play a role. So suppose we have, let's see, the orthonormal basis. We know that any vector H in the Hilbert space can be written in the form H is a sum from 1 to infinity, inner product of H with R sub k times vector R sub k. Theorem 5.4.5 says you have an orthonormal Schauder basis. This is how you represent vector H. Inner products is given, and vector quantities, the R sub k's. So here we have an infinite linear combination. This is how you express H in terms of that Schauder basis. Give me some wiggle room, let epsilon be greater than 0. The theorem we just stated showed us that when H has this type of representation, the norm squared of that vector H is the sum of the moduli of the squares of the inner products. The orthonormality plays a role in this as well. Maybe a passing observation. That means if we took the sequence of these inner products, norm squared, we get something summable. In particular, the inner product, H with R sub k, as k varies, forms a square summable sequence of complex numbers, or real numbers if the inner products happen to be real and the scalars are real. But anyhow, we're getting a square summable sequence. Square summable sequences live in little L2. So I expect to see little L2 play a role again here. Maybe not in this theorem, but it does in the last theorem, the fundamental theorem. But we've got this series, convergent series of real numbers is what this is. Even if the inner products are complex, then we've taken a modulus. So we're dealing with non-negative series of real numbers. So this is a convergent series. In fact, this is what it converges to, the norm squared of H. So there's some capital N, a natural number, such that when we take the index n greater than capital N, we have the tail of this series, that is the sum from k equals n to infinity. That tail must be small. Property of convergent series, the tails must be small. Let's make small epsilon over 2. So we're making the tail of the series less than epsilon over 2. Now we're going to introduce rational numbers and deal with the first capital N terms. So for k between 1 and capital N, there exists a rational number or rational complex number if we're dealing with complex scalars and complex inner products. Call that rational number a sub k, and we can make a sub k close to the inner product of h and r sub k. It's based on the denseness of the rational numbers in the reals, or the rational complex numbers and the complex numbers. So choose these a sub k's such that the modulus of the inner product of h with r sub k minus a sub k squared is less than epsilon over 2 to the k plus 1. So it's a two-step process, making the tail little and approximating the first several terms of this series with rational numbers, leading us to the following. The norm squared of h minus the sum from k equals 1 to capital N of a sub k times r sub k equals, well, h can be represented in terms of this series representation using the r sub k. So here's the Schauder basis representation of h. Now we've got some shared r sub k's, but this is a finite sum and this is a series. Well, let's try to combine these two over the finite sum, k equals 1 to capital N. So we'll peel off the first capital N terms of this, combine it in a sum with these terms. So we get a sum from k equals 1 to capital N, inner product times r sub k minus a sub k times r sub k. That leaves us with picking up at capital N plus 1, the tail of this series. Fortunately, we know that tail has been chosen in such a way that it's going to be small. Okay, there's a lot of orthogonality going on based on the fact that the r sub k's form an orthonormal sequence. So we can apply the Pythagorean theorem to, let's go back and look at that. We've got this vector plus that vector, norm squared. Think of it as a hypotenuse of a triangle. That's legitimate geometry. So the hypotenuse squared equals the sum of the squares of the two sides, as it were. So applying the Pythagorean theorem explicitly as stated is in theorem 5.2.3, it's stated exactly like this. We get norm squared of the first part plus the norm squared of the second part. These parts, the legs of the triangle, are at right angles to each other. Orthogonality is what we get based on the fact we started with an orthonormal basis. Now here, the orthonormality of the vectors, just a finite sum here, leads us to the fact that the norm squared is simply the sum of the coefficients of the r sub k's in modulus squared. So we can factor an r sub k out. We're left with this quantity here as the coefficients. The r sub k's are finite, no big deal. We just get the sum of the moduli of the coefficients squared, and that holds over here as well. As we've stated, when we have an infinite series of this sort with orthonormal vectors involved, we get a norm squared of this sort. Take the coefficients modulus of squared, and that's actually an equality there. We have chosen the a sub k's to be sufficiently close to the inner products such that it was epsilon over 2 to the k plus 1, I think it was. When we sum up all of these, we've got that bounded above by epsilon over 2. And we chose capital N in such a way that this tail of the series would also be bounded by epsilon over 2, giving us that the quantity we started with is less than epsilon. Let's maybe run back and look at the quantity we started with. It's got our eye on a sum of this sort. We took h minus the sum, a sub k, r sub k, where these a sub k's were rational or rational complex numbers. And we've got that norm, well, squared, less than epsilon. So I can balance this and make the norm itself less than epsilon for arbitrary epsilon, but this should suffice at this stage. So we took an arbitrary h in the Hilbert space, and we found a sum of this sort where the a sub k's are rational, or rational complexes, and any h that was an element of this set within epsilon of that h. In other words, this set D is countable. Is dense in H, given the epsilon version of denseness. And what we have here then is a countable collection of countable sums. Rationals are countable. We're taking these finite sums as n ranges over the rationals. And so we're producing rationals. We're producing a countable set as well. So it's dense, it's countable, and therefore H contains a countable dense subset. That is, H is separable, as claimed. Back to the notes. Okay, we're working our way up to my favorite result in all of this stuff. What an infinite dimensional separable Hilbert space looks like. Let's describe or define a Hilbert space isomorphism. Suppose H1 and H2 are Hilbert spaces. If there exists one-to-one and onto linear mapping pi from Hilbert space H1 to Hilbert space H2 that preserves structure, okay, the linearity is part of the structure. Another part of the structure is the inner product. So we're requiring that mapping preserve inner products. That is, the inner product of H with H prime in Hilbert space H1 equals the inner product of pi of H with pi of H prime in the Hilbert space H2. So whatever inner product we get in H1, pi maps us to a corresponding inner product that's equal in the other Hilbert space H2. Pi is called a Hilbert space isomorphism, and H1 and H2 are said to be isomorphic. Yet again, an isomorphism is a one-to-one and onto mapping that preserves structure. The structure is the linearity, because these are linear spaces, along with the inner product. So it preserves the linear combinations and it preserves inner products. The more structure we add, the more details it takes to be preserved in an isomorphism between these structures. Now we've got the equipment to state and prove, it's actually not hard with all the stuff we know at this stage, what I call the fundamental theorem of infinite dimensional vector spaces. The statement of which is that H be a Hilbert space with a countable infinite orthonormal Schauder basis. Then H is isomorphic to L2. So when we looked at the fundamental theorem of finite dimensional vector spaces, we said, vector space, you give me the scalars, the dimension, I'll tell you the vector space. It's Rn. If the scalars are real, the dimension is n, it's Rn. If the scalars are from field F and its dimension n, then it's Fn. Here, we're classifying infinite dimensional vector spaces, but granted, there's a layer of detail added. That detail is requiring them to have a countable infinite orthonormal basis in the sense of Schauder. All these notes are made out where we're in the infinite dimensions. We're looking for Schauder bases. So it's understood when I say basis, I mean in the sense of Schauder. With that layer of detail, then we can classify infinite dimensional Hilbert spaces with a countable Schauder basis. They're isomorphic to L2. So every infinite dimensional vector space with this little bit of detail here is isomorphic to L2. This little bit of detail gets you a space that's unique, and it gets you a space that behaves a lot like Rn. We can represent linear transformations with matrices in these spaces. For example, that's a property of Rn. They're infinite matrices because these are infinite dimensional spaces. Let's go through a proof. As I said, it's actually not that long. So we want to take Hilbert space H, show it's isomorphic to L2 by finding a mapping from H to little L2 that is one-to-one onto linear and preserves inner products. So start with the orthonormal basis, R1, R2, and so forth, of Hilbert space H. It was assumed to have a countable infinite orthonormal basis in the sense of Schauder. So let R be that basis. For H in the Hilbert space, define pi of H to be the sequence of inner products of H with the elements of R. So we're defining pi of H to be, pi of H to be the sequence, first term, second term, and so forth, of inner products, H with R1, inner product of H with R2, and so forth. We know Theorem 5.4.5 told us that, hey, these terms are the coefficients we would use in a representation of vector H with respect to that Chowder basis, that basis R. That is, H equals the series of inner products times vectors R sub k. Also, we saw, I mentioned this in passing in Theorem 5.4.7, we saw that if we take the the modulus squared of these coefficients, that gives us something that equals the norm of H squared. In particular, it's finite. That is, this sequence lives in L2. If you will take modulus, square those, add them up, you'll get the norm of H. Well, that's finite, and that's the requirement to be square summable, and that's the requirement for this sequence to be an element of little L2. So this is indeed first off, a mapping from Hilbert space H to L2. And we've got the theoretical background to say you put an H in and we get an element of L2 out by that mapping. Also, this isn't mentioned verbally here, but this is based on inner products. So we've got the linearity. We're good with the linearity. If we take pi of a linear combination, we'll get a linear combination of the pi's, as it were, based on the fact that we add things in L2 component-wise. So first off, pi is, in fact, linear. It maps us from the right place to the other right place. So we need to worry about one-to-oneness, onto-ness, and preservation of inner products. Well, now this representation of H in terms of the basis elements is unique. Bases give unique representations of vectors with respect to those bases. So for any given H, the coefficients are unique, and so the entries in this sequence are unique. In other words, pi is 1 to 1. You put two different vectors in, you'll get two different series out. They have to differ in some entry. So there's the one-to-oneness. We're left with onto and preservation of inner product. So choose an arbitrary element of L2. We want to show it's the image of something in the Hilbert space under pi. So take a sum from k equals 1 to infinity of a sub k modulus of squared. So we're choosing the sequence A1, A2, and so forth to be a sequence in L2. That is, it is square summable. I need the moduli if we're dealing with complex numbers. So that's on the table as well. Take this, consider the partial sums of this series. So we're going to consider the series sum from k equals 1 to infinity, a sub k, r sub k. So we've taken the components, as it were, of this sequence in L2 and made them coefficients of the basis vectors. What we want to do is see, is this vector really an element of the Hilbert space? Well, consider a partial sum for this series. Then, if we take indices m less than n, say, I need one to be bigger than the other because we're going to look at a difference of partial sums for that series. We're going to show this is Cauchy, and so we get the convergence. Notice these live in the Hilbert space, right? This is a sequence in L2, and this thing here, if it converges, it's an element of the Hilbert space. It relates to the vectors, and these are just scalars. Scalars in little L2, vectors in the Hilbert space. So when we take the partial sum S sub n minus the partial sum S sub m, that's the reason we needed this relationship between m and n, we get the sum from m plus 1 to n. The first m terms cancel out as common between these two partial sums. So we get m plus 1 to n is a difference of the partial sums. We took the norm squared, so we'll get a norm squared here and an equality. The r sub k's, those are all orthogonal. They're also unit vectors. It's an orthonormal basis. So the orthonormality allows us to write the norm squared of this vector as the sum of the moduli of the coefficients squared. Very much a Pythagorean type thing there as well, using the orthonormality of the R sub k's. Now, the sum from k equals 1 to infinity of the norms of the a sub k squared, the whole series, that converges. Right? That's how we started this conversation on this slide. It's an element of L2. So this series converges. So the sequence of partial sums of this series converges. Why? That's what we're looking at ultimately here. We got to it through going through vectors, but if we look at the sequence of partial sums for this series, must be convergent and must be Cauchy. But that means we can make this as small as you want by making m and n sufficiently large, by considering this series in L2. Well, if this is small when m and n are sufficiently large, then this is small when m and n are sufficiently large. But this deals with vectors, not sequences. That is, the partial sums for this series in the Hilbert space, the sequence of partial sums must be Cauchy. The sequence of partial sums S sub n in the Hilbert space must be a Cauchy sequence in the Hilbert space. But in Hilbert spaces, Cauchy sequences converge. So this sequence of partial sums must converge. In other words, this series converges in the Hilbert space. So if we were to take this thing now that we know to be an element of the Hilbert space, you apply pi to this, it'll produce the sequence a sub 1, a sub 2, and so forth. That's how pi was defined in terms of the mappings. We deal with inner products, and you'd pick off these coefficients as the inner products and as the terms of the sequence. So pi is onto. We took this sequence. What's mapped onto it? This element of the Hilbert space. Just needed to take care of some details and make sure this element, this thing here really is an element of the Hilbert space, that this series converges in the Hilbert space. It does through some Cauchiness arguments. Pi maps this onto that, and there's your onto-ness. So linear, because the mapping is defined in terms of inner products. A few details omitted on that, but it is linear. One-to-one, as observed on the previous slide, based on the uniqueness of representations with respect to bases. Onto by this, finally, preserves inner products. So take H and H prime to be in the Hilbert space. We know they have representations with respect to the orthonormal Schauder basis because it's a basis. So represent H as this kind of series involving the R sub k's, H prime, this kind of series. We use A sub k's for coefficients for H, A sub k primes for coefficients of H prime. Then take the inner product of H and K. That would be the inner product of this series with that series. Take that inner product, use continuity of the inner products. What we will get from that by the orthonormality is a sum from k equals 1 to infinity of a sub k times a sub k prime. So this series comes out. Hey, that scalar is what we would get in L2 by taking the inner product on L2. It's like a regular dot product, except for the infinity thing. We take the inner product of the sequence of A1s with A1s, A2s with a sequence of A1 prime, A2 prime. How you would define an inner product in L2 on these two sequences is exactly as that. Then that means we've got the inner product of pi of H. Pi of H would simply pick out the coefficients of this representation with respect to the orthonormal basis as a sequence. Gives us something in L2 that we've established. Pi of H is this sequence. Pi of H prime is this sequence. And we've got the inner product of H with H prime is the inner product of pi of H with pi of H prime. So that's the last piece of it. That means pi preserves inner products. It's a linear one-to-one and onto mapping that preserves inner products. It's a Hilbert space isomorphism. Pi is a Hilbert space isomorphism. H is isomorphic to L2. And I know what a separable Hilbert space looks like. A separable Hilbert space is isomorphic to L2. Preferably a Hilbert space with a countable infinite orthonormal Schauder basis is isomorphic to L2. So very much, I claim, fundamental theorem of infinite dimensional vector spaces tells you what these kinds of Hilbert spaces look like up to isomorphism. They look like L2. So it's an oversimplification to simply say that an infinite dimensional vector space is isomorphic to L2, because it's not, but an infinite dimensional vector space with the appropriate added hypotheses, separable, if you like, or countable infinite orthonormal Schauder basis. Remember, Schauder is the understood setting in these notes. That's why you're interested in separable Hilbert spaces. Well, really, you're interested in separable Hilbert spaces because of the basis stuff, not the separable stuff. They're equivalent. I know previous theorem, 5.4.8 told us that, but it's really the basis stuff that's interesting. It's not the separability stuff. That's just a single word without having to express all this. Yeah, it's equivalent to this. This is the important idea that makes separable Hilbert spaces a big deal. So I can tell you what an infinite dimensional vector space looks like with a few added details, and that's exactly the details. Final comment. Hey, if we had mappings in finite dimensions, linear transformations from Rn to Rm, they're represented by matrices. And I promised you that when we got to this infinite dimensional setting, all the stuff you can do in Rn, you can do in this infinite dimensional setting in these Hilbert spaces with Schauder bases. A theorem without proof is, so proof is quite similar to the way you would do it in sophomore linear algebra. It says if T is a linear transformation from Hilbert space H1 to H2, requiring these to have the same scalar fields, and these to have countable infinite Schauder bases, then T is equivalent to the action of an infinite matrix, A sub ij, I and j ranging over the natural numbers. Same thing as in finite dimensions, except the matrices are infinite matrices now. Everything's countable, so we're good to go. And you would find those matrices in the usual way by applying the transformation to basis vectors and then writing those in terms of elements of L2. Is how you do it. And that's where the matrices come from. So told you so, things from finite dimensions carry over to infinite dimensions if you add enough details. The details were the Schauder basis stuff. I want an orthonormal Schauder basis. But I wouldn't be surprised if some weird stuff doesn't happen in infinite dimensions. And that's what the last comment here is. So many of the properties of Rn carry over to this infinite dimensional Hilbert space, which is up to isomorphism. It's L2. I've been through many times this idea of a vector as having magnitude and direction. That's not what a vector is. A vector is what a vector space says a vector is. And it doesn't say anything about magnitude and direction. There must be vector spaces out there that don't have norms on them, though we've studied normed linear spaces, normed vector spaces. And when you say magnitude, you mean the norm, but there may be vector spaces that don't have norms on them. There are vector spaces that don't have norms on them. So I got to drop this idea in general, but it is a useful idea of thinking of vectors as magnitude and direction. You do that in physics, at least sophomore level physics, classical physics. You do that in sophomore linear algebra. Vectors have magnitude and direction. Turns out you can do that in little L2 as well. We've imposed enough conditions on these spaces that this idea of magnitude and direction carries over. So I want to do a little trick. Think of, and let's have this conversation explicitly in L2. So I talk about, kind of like infinite tuples in L2 versus n tuples in Rn. The directions idea in Rn kind of makes sense because, hey, in Rn, you've got the basis of a first vector, a second vector, and so forth. And these vectors are mutually orthogonal, right? In 3 dimensions, you get the ijk vectors, and that works in n dimensions. I'd sort of think of those vectors in the standard basis of Rn as pointing along axes. They're unit vectors, and think of them as pointing along axes. They're orthogonal to each other. That's fine in Rn. In Rn, I got no problems. This is what you mean really by direction. The direction idea never gets a formal definition, but you sort of think about it in 2 dimensions. I got left, right, and up, down. In 3 dimensions, we've got left, right, forward, back, and up, down. In 4 dimensions, we've got those first 3, and then maybe like a hyper up, hyper down, and so forth. So visualization doesn't work, but the manipulations are easy enough. But it's these orthonormal bases that contain the idea of direction, and writing directions as combinations of the fundamental directions. That's why they're bases. Well, we can do that in L2. We could kind of think about L2 as having a left-right direction, a forward-back direction, an up-down direction, another direction perpendicular to those 3, another direction perpendicular to those 4, and so forth, but without ending in little l2. Little l2 being, of course, the collection of sequences of, let's have a conversation about real numbers here briefly, square summable real numbers. If they're real, I don't really need those absolute values on there. If they're complex, I would, but here's little l2 and with real scalars. And I do want to think about those vectors in the orthonormal basis as representing directions. Now let's do something really weird. Let's take some properties that do hold in Rn, they're topological properties, that don't hold in infinite dimensions, that don't hold in little l2. And I can draw pictures because I can kind of visualize little l2. Well, my pictures are going to be in R3, but they're pretty legitimate in little l2 as well. So consider the set. Here we're taking actually the vectors in an orthonormal basis, but treating it not so much as a basis, but as simply as a set. And I think of it as a set of points. We could associate them with vectors by putting those vectors in standard position, the usual approach to a geometric interpretation relating vectors and points. Take this set R consisting of, if you like, these points in L2. Certainly it's a subset of L2. It's closed in the topological sense because if you look at any 2 of those vectors, they're square root of 2 apart. So actually it's a collection of isolated points that don't have a limit point. It's a closed set. Its complement is open. You take something in the complement, I got plenty of room to find a little open ball that doesn't intersect any of these things. So this is a topologically closed set. We'll draw a picture here in a second. It's a bounded set. All those vectors are unit vectors. So they're all distance 1 from the 0 vector, the origin, if I interpret them in terms of points in standard position. So we got ourselves a closed and bounded set. Heine Borel would tell you, if we were in finite dimensions, that closed and bounded set should be compact. That is, every open cover should have a finite subcover. But that's not the case for this set, and it's not the case for a very geometric reason. Suppose we take this first point or vector and cover it with an open ball of radius 1/2. Cover the second point with an open ball with the point as its center of radius 1/2 and so forth. That's an open cover of this set because every point is a center of one of those open balls. We get a picture that looks something like this. Well, here's the first 3 directions. So we'll go to the point the vector 1, 0, 0, 0, 0, 0, and we'll draw a little ball around that of radius 1/2. Go to the vector 0, 1, 0, 0, 0, 0, put a ball around it of radius 1/2, 0, 0, 1, 0, 0, 0, 0, and so forth. Now, these balls are disjoint. There's no intersection. It's a distance square root of 2 measured in L2 between these two vectors, these 2 points. And these have radius 1/2. So the balls are disjoint. They don't intersect. Their centers of those balls are too far apart. We made the radii sufficiently small. Also, that means, hey, any one of these open sets contains exactly one element in set. I call this set R, just like we did the basis. So we've got a closed set. All those blue points form a closed set. It's a bounded set. All those blue points are distance 1 from the origin, the 0 vector. Strictly speaking, they're vectors, not points. But I can give a geometric interpretation by putting them in standard position. Closed and bounded set, and we got an open cover. Heine-Borel would tell you in Rn, every closed and bounded set is compact. That is, every open cover has a finite subcover. This closed and bounded set in L2, and it is infinite dimensional Hilbert space, does not have a finite subcover. Because if you leave off any one of these open sets, you no longer have an open cover, because this point is in only one of the open sets. It's in this one. Now, how do we pull this off? This is a closed and bounded set. It's not compact. Yeah, because it's in infinite dimensions. You can do that in infinite dimensions. That's one of the weird things that happens in infinite dimensions. Heine-Borel doesn't work in infinite dimensions. We did prove that every compact set is closed and bounded, but there exist closed and bounded sets which are not compact. They don't exist in finite dimensions, but they exist here in infinite dimensions. So this open cover has no finite subcover, not a compact set. What really made this work? It's all the directions. You were able to put a sphere here and a sphere there and a sphere there and go in another direction perpendicular to these and add another sphere, go hyper up, and another direction and add another sphere. You took advantage of all the directions. We never went far from the origin. We never went more than a distance of 1 from the origin or the 0 vector. But it's the directions that made this weird little thing happen. And we were able to go in all these different directions, pick these points. They're sufficiently far away from the other points because of the directions. They're always square root of 2 apart from each other and always distance 1 from the origin. That allowed us to create a closed and bounded set. It's really the boundedness that we use the directions on. And the closeness, keeping these things separated from each other. It was that allowed us to create a closed and bounded set in infinite dimensions that is not compact. You try to do this in 3 dimensions. Now, I've kind of run out of fundamental directions. I start adding more points that are only 1 unit away. Well, they're going to cluster around each other, and this just isn't going to work in finite dimensions. In a very crude sense, that's why the Heine-Borel theorem holds in finite dimensions. Weierstrass's theorem says in Rn, probably you were exposed to it in R1, an infinite bounded set has limit points. That's Weierstrass's theorem. It's used to show every bounded sequence has a convergent subsequence, Weierstrass's theorem. But it doesn't hold here. Here we have a infinite bounded set in L2 that doesn't have a limit point. The points don't cluster. Yeah, they don't cluster. They're always square root of 2 apart from each other. It's an infinite set. We made it infinite by taking advantage of the directions. And so here's a set that also violates Weierstrass's theorem. Weierstrass didn't say it was going to hold in infinite dimensions. Weierstrass holds in finite dimensions, and so does Heine-Borel. So there's some exotic things that happen in infinite dimensions. Topologically exotic. They're just surprising. They violate your experience in finite dimensions. But that's some funny stuff that can happen in infinite dimensions. And it's not really that funny. It's a different behavior from what happened in finite dimensions. But we've imposed a sufficient number of constraints so that this infinite dimensional space, it's mostly acting like things do in finite dimensions. The linear algebra stuff has survived this transition to the infinite dimensions. If you'll let me take infinite linear combinations, that is, we talk about linear combinations in the sense of a Schauder and in the sense of a Schauder basis, and you'll let me use infinite matrices, then I can basically preserve most of linear algebra into these infinite dimensions. Just some surprises pop up in these topological results, like the Heine-Borel theorem and Weierstrass's theorem. And that's what happens in a neat infinite dimensional space. It behaves just like Rn, but you have to slather on this layer of details, this idea really of an orthonormal basis and the idea of basis in the sense of Schauder, infinite linear combinations. Makes sense, you're in an infinite dimensional space. And that's my favorite part of functional analysis. So we'll move on to something a little more mundane next, but that takes care of this section, and I will see you later. Have a nice day.